Welcome back to the Deep Dive. So if you've spent any time learning to code, you probably know the standard roadmap, right? So you start with HTML, maybe a bit of
Right, then
CSS.
maybe a front-end framework, build a basic CRU'd app.
Exactly. Maybe automate some simple task. It feels like the safe, sensible path.
It is, yeah. It's often the path of least resistance. But, those projects, they don't always force you to deal with really systemic complexity. They teach you skills in isolation, sure, but they don't demand that deep integration or serious performance optimization or real architectural thinking right from the get-go.
And that's precisely why we're diving into this today. We're looking at sources that put forward this, well, kind of counterintuitive idea.
Which it is.
That building games isn't just some fun little hobby for creative types who code. It might actually be the single best, fastest crash course out there for mastering really high-level programming skills.
Yeah, the core argument, and it's pretty convincing when you look at the source material, is that the second you decide to make even a simple 2D game, I mean, think Flappy Bird, or like a basic Pong clone,
Right, something seemingly simple.
you're instantly hit with almost every major problem that large-scale software teams face. You've got real-time input, you need strict rules for structure, you got to manage memory, solve performance issues, often all at the same time.
So the goal here isn't necessarily to become a pro game developer, though that's cool too. It's more about seeing these projects as like a pressure cooker. They just dramatically sharpen your skills across the board. Even making a character jump correctly forces you into some pretty advanced concepts. Okay, let's unpack this, starting where all good software starts, structure and architecture.
Right. We have to begin with what the source calls thinking in systems. Traditional tutorials, they often have you write maybe one big script that tries to do everything
Yeah, I've seen those.
in a game. That falls apart immediately. It's just unworkable. You instantly see you're juggling multiple independent systems that have to cooperate without tripping over each other.
Okay, so give us some examples. What kind of systems are we talking about?
Well, you've got your rendering system, right? Its
Right.
only job is drawing stuff to the screen. Then there's a physics system manages movement, collisions, gravity, all that, and an input system, just listening for what the player's doing with the keyboard or controller.
So the key insight there is that these systems have to be decoupled.
Yeah.
Like, I need to be able to completely change how physics works
Yeah, maybe swap out a basic collision check for something way more precise.
without breaking how the score is displayed or how the enemies decide where to move.
Exactly right. If you can manage to change your player's sprite without messing up the code that calculates their position, you've basically nailed modular design. And that mirrors enterprise architecture perfectly. You're practicing defining clear APIs, clear boundaries between different parts of your code, different services. It makes sure things are maintainable, scalable, even possible to work on later.
This sounds good, but doesn't building those separate systems push a learner straight into something quite complex, like the Entity Component System Pattern, ECS?
That's a fair point.
For someone starting out, isn't ECS kind of overkill compared to just simple object-oriented inheritance?
It can seem that way, and yeah, lots of people start with inheritance. You might have a goblin class that inherits from enemy, which inherits from movable thing, that kind of structure.
Right.
But the problem with those deep inheritance trees, they get fragile and complicated super fast. What if you want a static object like a lamp to have hit points, but it shouldn't move?
Yeah.
Yeah.
You either break the chain or inherit a bunch of movement methods you don't need.
Which is instant technical debt right there. ECS avoids this. It says an entity is just an ID, a placeholder. Then you attach these small specific data chunks called components, like a health component or a position component.
Yeah.
And the systems just operate on all entities that have the components they care about. Like the movement system only looks at entities with position and velocity components.
So it keeps the code much flatter, more decoupled.
Extremely decoupled. And, if you're a front-end dev using something like React, you already think in components for your UI.
True.
Building games forces you to apply that exact same scalable component-based thinking to your game's data and logic, not just the visual parts.
Okay, so that reframes ECS. It's not some obscure game thing. It's actually a really important habit for managing complexity anywhere. What about the actual game loop? Every game has that core loop, right? Check input, update state, draw.
Right, you check input, you update the world state, you draw the world, and repeat, and you notice that repetition very quickly. And that's where you're naturally pushed towards abstraction. The constant need to handle input, check collisions, update animations, frame after frame. It forces you to turn those messy, repeated bits of code into organized, reusable functions or classes, maybe even tiny frameworks.
So you stop writing, if player hits A, move left 5 pixels in 50 different places.
Please, yes.
You write one solid input manager.get horizontal input function or something like that.
Precisely. And that discipline, the act of building reusable game loops, input handlers, maybe even a mini engine for yourself. It's the same fundamental skill professional developers use when they design internal tools or public APIs or SDKs.
Because the game itself punishes lazy structure.
Instantly. The cost of spaghetti code isn't some abstract future problem. It's immediate visual failure right there on the screen. Lag, bugs, crashes.
Okay, so structure is vital. But a perfectly structured game is useless if it, well, grinds to a halt or feels laggy. Which brings us to the relentless pressure games put on speed. Performance.
Yeah, and the contrast here is really stark. You know, a typical business app might be okay with a response time of, say, half a second for a big database query.
500 milliseconds, sure. Usually fine.
In a game, you're on the millisecond test, a super strict budget. If you want a smooth 60 frames per second, you have about 16.7 milliseconds.
16 milliseconds to do everything.
Everything. Update physics, process all player input, run the AI logic, draw the entire scene to the screen, all of it.
Wow. And if you miss that budget?
Frame rate drops, it stutters, the user experience is just ruined. Lag is this immediate, glaring failure.
So it forces you to write code that's not just correct, but genuinely fast.
Exactly. You're constantly thinking about memory usage, CPU cycles, I/O waits. You're not just learning about optimization from a book. You are living the painful consequences of inefficient code every single frame.
Can you give a concrete example, like an optimization instinct that games really hammer home?
Sure, take loading assets, like textures. A beginner might load the image file for, say, a tree every single time they need to draw a tree on screen.
Okay. Seems logical at first.
But loading files from disk, or even just copying big chunks of memory around, that's a huge bottleneck. It eats up precious milliseconds from your frame budget.
Right.
Games instantly teach you about asset management. You load that tree texture once, maybe when the level starts, stick in memory, and then just reuse the reference, the pointer to that data whenever you need to draw a tree.
So that instinct, check the cache before hitting the disk or optimize database queries in a web app, that directly comes from the pain of seeing your frame rate tank because you loaded the same tree image 50 times.
Absolutely. That pain is a very effective teacher. And performance ties directly into responsiveness, especially with event-driven code.
Okay.
Games are fundamentally built around discrete, real-time events happening. A button press is an event. A collision between two objects is an event. An enemy spawning, a timer hitting 0, all events.
So if you've ever, struggled to really get your head around asynchronous code, maybe promises in JavaScript or handling message queues on a backend.
The game loop is the perfect practical teacher for that. Every single thing the player does, jump, shoot, switch weapon, it's an event you have to listen for and react to instantly.
Without blocking the main loop.
Crucially, yes. You quickly learn about the asynchronous nature of things, how to process these events without freezing the screen, how to manage state changes when multiple things might be happening at once. It gives you this deep, hands-on feel for event listeners and non-blocking I/O that makes async programming in other areas feel much more natural later.
And there's that hyper-focus on input responsiveness too, right? Making the controls feel instantaneous.
Totally. You're learning how to handle complex inputs, maybe from different devices, how to debounce a button press so one tap doesn't accidentally register 20 times, how to accurately detect when multiple keys are pressed at the exact same time, that kind of precision.
And that attention to detail changes how you see interaction everywhere else.
It really does. You stop seeing, say, a button click in a web form as just capturing data. You see it as the start of a feedback loop that needs to feel immediate, natural, satisfying for the user. That focus translates directly into designing faster, smoother interactions in any application you build later on.
Okay, let's shift gears a bit. Let's talk about the advanced skill boosters, the things maybe developers often try to avoid or only learn theoretically, but games make really practical and, well, mandatory.
We absolutely have to start with debugging. The source material calls it managing structured chaos, which I think is perfect.
Structured chaos.
Yeah, because games are just full of moving parts, right? AI, pathfinding, physics calculations, unpredictable user input. They all interact in complex, often unexpected ways. And this leads to the most baffling, frustrating bugs you can imagine.
You mean like the character phases through the wall, but only if they jump exactly twice facing left
Yeah.
while holding the shift key?
Precisely that kind of bug, the ones that seem impossible to reproduce. And that specific kind of chaos, it forces structure onto your debugging. You can't just panic and change random things.
Right.
You develop patience. You learn systematic thinking to actually reproduce those weird edge cases. You learn to isolate the problem by commenting out systems one by one. You learn to flood your code with meaningful logs and assertions.
It's fascinating because the source highlights that this experience makes you the kind of developer who doesn't freak out later. You've already wrestled with code far more chaotic in your game project than you might ever encounter in a typical corporate code base.
Exactly. And this leads nicely into another area developers sometimes avoid, the math that actually matters.
Math.
Yeah, most developers, unless they're maybe in data science or something very specific, tend to shy away from, say, advanced geometry or trigonometry.
Sure, you don't often need sine waves for a CR8 app.
But in game dev, suddenly that math isn't theoretical anymore. It's essential to make your thing work at all.
Wait, so you're saying developers who normally avoid math suddenly find themselves needing, like, vectors and trig just to make a spaceship fly in a straight line or an arrow arc properly?
It's pretty much mandatory. You need vectors for movement and projectile motion. You need geometry for collision detection, figuring out if two shapes are overlapping. You need trigonometry to make things rotate smoothly or move along a curve.
And the key is you're not learning it from a textbook formula.
No, you learn it by typing it in, hitting run, and immediately seeing the visual result on screen. Oh, that vector made it fly sideways. Okay, need to adjust. That hands-on visual feedback loop gives you a practical confidence with those mathematical concepts that helps immensely later when you tackle complex algorithms or data visualizations in any field.
That jump from abstract theory to painful practical necessity seems really key. But games also sharpen your design and UX instincts, right? Even if you don't call it UX at the time.
Definitely. Good games just feel right. And that feeling isn't an accident. It comes from meticulously tuning tiny details.
Like what?
Like the exact height and arc of a character's jump, the tiny delay before a weapon can fire again, the satisfying little ping sound and visual effect when you collect a coin. You're constantly tweaking these things, learning about feedback, about making actions clear and rewarding, essentially learning UX principles through practice.
So you end up building systems that aren't just functional, but also genuinely engaging and clear. And that skill transfers directly to making, say, a banking app less frustrating and more intuitive.
Absolutely. Users feel acknowledged, they understand what's happening, it makes any interface better. And finally, there's creative problem solving.
Telco.
Games rarely have a single right way to build something. The problems are often unique, and the performance constraints mean you need unconventional solutions. You might need to figure out how to fake realistic-looking physics without doing super complex, CPU-heavy calculations.
Or make the AI seem really smart using clever tricks and simple state machines, rather than some heavyweight algorithm.
Exactly. It's the ultimate test of finding clever, efficient workarounds. It trains you to be resourceful, to think outside the box when faced with what seems like an impossible feature request or a tough production bug. Because often the game engine itself just tells you, nope, you can't afford to run that complex logic 1,000 times a second.
So you learn to be ingenious.
If you tie all these threads together, the systems thinking, the performance obsession, the debugging chaos, the practical math, the UX tuning, the creative problem solving, you see the learner is getting this incredibly broad exposure.
All driven by one unifying, motivating goal: just make the game playable and fun.
Right, which means building games really is this accelerated crash course. It produces cleaner code, better systems thinking, and sharpens your sense for performance and design in a way that, frankly, building yet another to-do list app just doesn't.
And you get that huge added bonus of motivation. It's fun. Seeing your own creation come to life is incredibly rewarding.
And the source material really drives home one final powerful point we should probably leave the listener with. The most valuable lessons, they don't come from just reading books or following tutorials step by step. They emerge from those moments where you struggle with a really weird bug, where you test 5 different ways to optimize something, where you build something that actively teaches you back by failing right there on the screen until you fix it.
That's a fantastic point.
Yeah.
So if your programming journey so far has been mostly, sticking to those sensible CRU apps or basic websites, maybe the challenge is to try something a bit messier, something more chaotic, something profoundly creative. Give it a shot. Challenge yourself to build even a tiny game, maybe this weekend. You might just be amazed at how quickly your fundamental coding skills level up and how much faster and more confident you become at tackling complex, real-world problems down the line.